Okay, so we are going to talk about solving and graphing radical functions. So we're going to graph this equation, y equals the square root of x plus 5 minus 2. And there's a couple ways to do this, and we are definitely going to reference our transformations in the process. But a good method is to think about some of the points that you might want to plot. So I am going to just draw my little table of values there. And I know that I would really like to get under my square root, I'd like to get 0, I'd like to get 1, I'd like to get 4, and I'd like to get 9, because those are all values that I can square root very nicely. So let's think about what I have to put in for x so that I get 0 under the square root, and that would be -5. That would give me that 0 under the square root. What I would have to put in to get 1 under the square root, I'd have to put in -4. It's -4 plus 5 would give me 1. I would really like to get 4 under the square root, so I'd have to plug in -1. And then I would like to get 9 under the square root, so to get that I'd have to put 4. And then as I plug these in, when I get 0 under the square root, I get -2 for y. When I plug in -4, I get -1. When I plug in -1, I get square root of 4 is 2, minus 2 is 0. And then when I plug in 4, I get 3, and 3 minus 2 is 1. So I can go and start plotting these points. 1, 2, 3, 4, 5. 1, 2. And then 1, 2, 3, 4. -1, 0. And 1, 2, 3, 4, 1. And then I know that my graph should be connected with a smooth curve as best as I can. And it's only going to continue in one direction because we can't plug in any numbers that will give us a negative under the square root, because those will have imaginary outputs, and this is a real coordinate grid, so we can only have real values on here. So once I've done that, I just want to double check that this makes sense with my transformations. When we have this plus 5 with the x here, that should mean that my graph shifted from 0, 0 being the endpoint to the left 5, which it did. And then this -2 here should mean that it shifted from 0, 0 down 2. So I'm shifting over 5 down 2, and there is my graph. It did shift accordingly, so I know it makes sense and it's correct. So next we want to come up with our domain and our range here. And I look at my x values. Looks like my lowest x value is this -5, and then all my x values are bigger than that. So my domain is going to be all the numbers greater than or equal to -5. Another way to write that, if I'm using interval notation, is to say from -5 to infinity. And then my range, going back to that same point, my lowest y value is -2, and then it continues up from there. So y has to be greater than or equal to -2, or another way to write that is to say from -2 to infinity. So we're going to do another one, and the strategy is very similar. We want to plug in some inputs, and we want to pick those strategically to make sure that we're getting numbers that we can simplify ourselves. So I know that good values to get under a cubed root are going to be -8, -1, 0, 1, and 8. So I'm going to figure out what do I have to plug in to get those values. So x would have to be -9 for me to get -8 here. So I'm going to plug in -9. X would have to be -2 to get -1 under the cubed root. And to get 0, I'd have to have -1. To get 1, I'd have to have 0. And to get 8, I would have to input 7. So again, I'm trying to figure out what goes into x so that the x plus 1 gives me these things. just picking some strategic values here. And so then I'm going to plug those values in. So my output, if I plug in -9, I get -8 under the cubed root. The cubed root of -8 is -2 times -1/2 is +1. When I have the cubed root of -2 plus 1, that's the cubed root of -1. So that is times -1/2 is +1/2. When I get 0, when I plug in -1, I get 0 as my output. When I plug in 0, I get -1/2. And when I plug in 7, I get -1. So again, picking selective values to make sure that my graph makes sense. And now I'm going to plot those. So here's one of my values. Oh, I'm not sure what I just did over there. That should be, what was that going to be? -1. Okay, so there's 1 point, -2, 1/2, -1, 0, 0, -1/2, and then 7, 1, 2, 3, 4, 5, 6, 7, -1. So I am going to connect those with a smooth curve, and it's kind of hard to do that on the iPad, so bear with me there. Looks approximately like that. I didn't do the best job right here, but that's okay. You guys get the picture. So we're going to identify domain and range here. And so because I can tell that this graph is continuing to infinity over here to the left and continuing to infinity over here to the right, my domain is going to be all real numbers. And my range looks like, because this will be continuing up forever and ever, it'll continue slowly, but it will continue forever up. This one will continue forever down forever, and so that really will be hitting all numbers as well. So that's all real numbers. Now we might ask ourselves if it's possible to find the domain and range of these types of functions without having to draw the graphs. And the answer is yes, because all of our cubic graphs have that same shape. They either look like this, right? They have that little curve like that, or they go the other direction like that. They might have a much taller or a much more narrow, even more narrow, but no matter what, it's continuing on towards infinity in both directions, in the x direction and in the y direction. So whenever we see that cube root graph, we know that both the domain and the range are going to be all real numbers because it's going to hit every value there. But we know that's not true with our square root functions, because our square root functions are always looking something like this, or when it's a negative in front like this, it's going to reflect it downwards and look something like that. So it's always going to start at some point and continue on towards infinity or negative infinity from there. So when I look at this, I have to figure out, based on my transformations, where that endpoint is. So I'm going to ask myself, where is this endpoint right here? And I can figure that out by looking at the transformations. So this transformation right here means that it's shifted to the right, 2, and this transformation means that it's shifted down 1. Remember that the y value always shifts in the direction of this sign, but the x value, it's x minus h, so our h value is just that 2, just like when we did quadratics. So it's going to shift to the right 2 and down 1. So that means that the very lowest x value we have is 2. And it's going to continue from 2 to positive infinity. Another way to say that is x is greater than or equal to 2. And then our range is over here, it's shifted down 1, so the y value, the lowest y value, is going to be -1. And because of this, because this is positive here, it's going to go from -1, because it's shifted down 1, up from there, right? Because this is a positive a value, it's going to travel upwards. It's not doing any kind of reflection. So that means that y has to go from -1 to positive infinity, or to say y is greater than or equal to -1. Now, if we look at this one here, it's very similar, but because of that negative, it's going to reflect that graph downwards here, right? So instead of traveling upwards like this one did, this negative means it's reflected downwards. And so when we look at that, we know that we are going to have all the y values less than that point. So looking at our transformed graph, we have to check out this and this again. This plus 2 right here means that it's shifted to the left 2. And this means that it's shifted up 5, excuse me. And so that means that our domain, because it's shifted to the left 2, so to the left 2 would be at -2, all the way to positive infinity. Or we could say x is greater than or equal to -2. And then our range is all the y values less than 5. So that's from -infinity to 5. Or to say y is less than or equal to 5. And it's less than because this negative has flipped it upside down and now it's traveling downward instead of up. So it is possible to find the domain and the range of these graphs without drawing them. We just have to keep in mind what transformations are happening. How did the shift affect this endpoint from 0, 0? And how does the a value affect the graph, whether it's traveling up towards positive infinity for y or down towards negative infinity for y? Now, in addition to graphing these radical functions, we also want to be able to solve them. And so the first thing that we're going to do when we see a problem like this one is we want to first write that power of 1/2. We know that that also is the same thing as saying the square root. So I'm just going to rewrite this so that instead of saying 6x plus 51 to the 1/2, I have the square root of 6x plus 51. And then I'm going to think about what is the inverse operation of square rooting, and that is squaring. So we are going to square both sides so that we can get rid of that root. But that does mean that when we square that x plus 4, we are going to have to distribute or FOIL that out. So when I distribute that, I get x squared plus 8x plus 16. Oops, it's not 16x, it is just 6x plus 51. And now this has turned into a quadratic, and anytime we have a quadratic, we want to get it set equal to 0. So I'm going to subtract 6x from both sides, and I'm also going to subtract 51 from both sides, so that on the right side, I'm left with 0. So that gives me x squared plus 2x minus 35 equals 0. And then I have a couple options to solve. I can solve by factoring, completing the square, or using the quadratic formula. And I like factoring the best if it can factor. So I'm going to see if it will, and it looks like it will. with a positive 7 and a negative 5. And then I can go ahead and finish solving from there. So I get that x equals negative 7 or x equals 5. However, we have to be very careful because we can't decide that either of those are a solution until we go back to the original problem and plug them in and make sure that they actually work. Because whenever we do something like square both sides of an equation or cube both sides, what we're doing is we're potentially creating extra solutions that may not work. So we always have to check our 2 or 3 or however many answers we get, we always have to check them. So I'm going to go ahead and plug in negative 7 for x. And I'm going to leave that as a square root instead of a 1/2 just so it's visually more clear. And so we get here negative 3 equals the square root of, and that will be negative 42 plus 51. So that'll say negative 3 equals the square root of 9. Now that's not true. The square root of 9 is positive 3. Not negative 3, so x equals negative 7 is an extraneous solution. It doesn't actually work. And before I can say that x equals 5 works, I need to plug that in as well. So I'm going to check that out. 5 plus 4 equals 6 times 5 plus 51. And that's really actually just under the square root there, but I'll do that on the next one. So the square root of 30 plus 51, now that is true because that says the square root of 81 equals 9, which is correct. So even though in the process of solving we got 2 solutions, one of them is extraneous and does not work, and so we only have one accurate solution for this equation right here. Okay, so we are going to look at a similar problem, but this one is a cube root problem. The process looks the same. Our goal is to start out by isolating the root. So I'm going to add 8 to both sides. And so that gives me the cubed root of p over 8 equals 6. And then in order to undo my cubed root, I'm going to need to cube it because that's the inverse operation. So that gives us p over 8 equals 6 cubed, and 6 cubed is 216. And then we're still solving for p, so I'm going to multiply 216 by 8 to get 1,728. And I think that is my answer, but before I can circle it, I am going to double check that it works. So 1728 divided by 8, which we know is 216. And the cubed root of 216 is 6. So that gives me negative 8 plus 6 equals negative 2, which is true. So p does equal 1728. It is not an extraneous solution. It is a correct solution. That's all for our solving and graphing radical equations. Go ahead and make sure you see me for extra help.